All right, well, welcome everybody. My name's Sean O'Connor. I'm the lead application engineer at Bitly, so that means I basically run the backend engineering team. And today I'm going to be talking about failure in distributed systems and kind of some methods for dealing with that. Before I dive into that, I usually like to get something out of the way. Usually people hear Bitly, like short links, really? How is that a business? Like that's, come on, this is silliness, is child's play. I could literally write a URL shortener before you're done with this talk. And even if I accept that doing that at a large scale and doing it in a highly available way is a non-trivial problem, how on earth do you make money doing that, right? Like, you can't actually make money off short links. And the short answer for us is a combination of branding. Oh, this is doing something funny. There we go, branding. So we host a bunch of custom short domains for pretty much any big name brand that you've heard of, and analytics. So basically we track every click going through our short links and do a whole bunch of analysis on that for both our free users and for paying customers. To give you kind of a sense of the scope of the problems we deal with, we see roughly 270 million redirects every day. It works out to about 8 billion a month. 26 million shortens, crawl about 4 million web pages, and we do that with about 400 servers spread across 2 data centers, about 20 engineers doing 20 plus deploys every day. So it's a bit of stuff going on. All right. So with that, kind of on to the main topic, right, of failure. Things go wrong, and it can get interesting, particularly with distributed systems, right? So distributed systems, we love them at Bitly, but what am I talking about? What is a distributed system, right? So here's a big, nice, verbose description of what distributed systems are. It's off of the Eternally True Wikipedia, but it was actually quoted from a book, so assumably that's correct. So let's kind of step through that real quick, just so we have a full context on what we're talking about here. So a distributed system is a software system in which components located on network computers communicate and coordinate their actions through passing messages, right? So a bunch of computers talking to each other, right? The components interact with each other to achieve a common goal, right? So they're not all just like doing their own thing and happen to be passing messages, right? They're all trying to accomplish some common task. And it has three significant characteristics of concurrency of components, right? So everything is able to work independently without having to wait for other things to do their own thing. Lack of a global clock. It's a bit of a fun physics problem for another talk, although somewhat related. And independent failure of components, right? So one piece breaks, the whole system shouldn't break. Sounds cool, right? Presumably you want some of this. But a lot of why it comes down to why you want some of this, and you look at something like distributed systems, is it lets you build faster, easier to scale, more robust systems at a lower cost than, let's say, some kind of more brute force approach of just like continually getting a bigger box, right? Cool. So let's say we're sold. We got our big fancy computing cluster going, right? Very modern hardware here. And everything's going great. And then one day something breaks and things, maybe have some side effects that we didn't account for. This guy is Leslie Lamport. He's kind of one of the big thinkers around distributed systems. He has this fantastic quote of, "A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable," right? That sounds kind of terrifying and miserable, doesn't it? It's just scary. So let's talk through a little bit of how things can go wrong, and then we'll kind of, once we're good and scared, we'll dive into how we deal with that, right? So one of the big categories of failures that you need to deal with in distributed systems is host failures, right? So like we talked through, a distributed system is a whole bunch of computers trying to do stuff, right? As we all know, computers fail, right? And they tend to fail, the failures tend to show up in two types, right? So there's the easy ones where hosts just completely fail, right? Like somebody unplugged the power cord, an EC2 instance went into whatever oblivion they go into, right? It's just completely gone, it's hard gone, everything that's there is no longer there. While that sounds horrible, in a lot of ways that's the really easy case because it's very clear what has happened. It's gone, you need to move on with life, right? There's a harder case of where things are just kind of broken, right? Let's say a request that normally, for whatever reason, let's say a hard drive is starting to fail, or you have a bad RAM chip or something, and all of a sudden a computer that normally was responding to requests in a few milliseconds are responding in minutes, right? It's technically not broken and dead. It's still responding to some requests, so you think it's alive. But for all practical purposes, it's broken and having all kinds of nasty side effects, right? So you have to figure out that it's broken-ish, right? The next major place where you start to see failures is in the network, right? And similarly there, you have an easy kind of failure, right? If your network cable looks like this, things are just not working. And again, that's fairly easy to detect and understand and work around. Well, work around may be more complicated, but at least know what's going on and where it's failed, right? But similarly, you can run into basically all kinds of crazy, weird, intermittent issues with networks, right? You can have just contention between just like the traffic on a given network is more than the capacity available, and it has weird side effects. You can also run into crazy things where for a little while we had this crazy situation where running a job on our Hadoop cluster was an off button for a random portion of our network. What it turned out being was there was an interaction between the switches in our data center and the NIC cards in some of our servers, where like once the throughput on a given Ethernet card went over a certain level, it would send this like flow control packet that would basically tell the switch to turn off its port, and that would like propagate to like the bridge, and so like it just would randomly turn off half of our network. It was kind of terrifying, and it was also one of those things where like when that happened, just like I don't even what, like it's just baffling, right? And so you have to try and have ways to deal with that, right? And kind of the last major place where things kind of fail and get squirrely in distributed systems is consistency, right? Since things are spread out over a bunch of nodes that have to communicate, and this is actually kind of related to that no global clock, having a consistent view from a system level perspective can be really hard, right? If server A thinks that a value is 1 and server B thinks the value is 2, you probably have a problem, right? And things are probably not going to work the way you expect. And if you're not careful, you end up just sitting there going back and forth and like, well, I don't know, right? It's just no good. And so, you know, it just can make you a little crazy. And then there's a bunch of other categories of failures that we're just going to kind of sweep under the rug and ignore this talk, because the ones we've mentioned so far, kind of your meat and potatoes, these are the ones you're dealing with every day in distributed systems. There's things that can happen like clock drift and other wackiness that you eventually need to deal with, but we're going to ignore for the course of this talk. All right, okay, so we're good and scared. A lot of ways we just want to say, nope, going home. In a lot of ways, if you can get away with it, right, if your problems can be dealt with on just a single machine, that's a great answer, right? If you can just avoid all these problems in the first place, thumbs up, do that. If you can't, let's figure out how we can get some confidence and get some tools for dealing with this, right? So one of the biggest tools that we lean on heavily at Bitly is asynchronous cues, right? And generally speaking, from a system level, designing systems to communicate in an asynchronous way whenever possible. Async is better than sync. Except when it isn't, but we'll get to that. So what do I mean by asynchronous versus synchronous, right? So what I mean is communication between systems ideally should look more like letters in the mail or email than two people having a conversation. And the reason, there's lots of benefits that you get from this, but particularly in the context of dealing with failure, the powerful thing about this is it's okay for letters to pile up, right? If you're having a conversation and the other person just, passes out, right, the conversation stops, right? You can't do anything until the other person comes back. If you're sending letters in the mail and let's say somebody goes on vacation for a week, it's okay. The letters pile up for a while and they come back and then things resume when they come back. It's okay. At the end of the day, it's not a magic bullet, right? You still have to deal with whatever failure happened on the other side, but it buys you time and flexibility so that you're going from like putting out fires and freaking out to just like, all right, it's okay. We got stuff we got to do, but we got time. We're okay, right? A particular tool that we've built to do this is a system called NSQ. It's not going to go super in depth with it. If you're interested in talking about it, I'm happy to talk about it more. But it's basically a distributed messaging system that makes it relatively easy to do a lot of this stuff. If you're interested, you can go to nsq.io, find out a bunch more. Of particular relevance is for this audience is a lot of the kind of cooler things in NSQ that, so NSQ basically provides a lot of the failure dealing with tools. Wow, that's a horrible sentence. Provides you with a lot of tools that we're going to talk about out of the box, but that happens in the client side of things. So at Bitly, Python's kind of our main language. Accordingly, the PyNSQ client is one of the more mature and sophisticated clients as far as dealing with failures. So check it out, GitHub, Bitly, PyNSQ, fun stuff. So the next kind of major technique that we have for dealing with failures and again, kind of keeping ourselves sane is timeouts, right? We're not talking about timeouts where like we're going to put the process in a corner and let it think about what it's done. While that would be entertaining sometimes, not super useful. We're more talking about having a way to prevent this from happening, right? Of having one failure from cascading throughout the system, right? So let's think about that awful type of failure I was talking about, where those intermittent, like, things aren't technically broken, right? Like you'll send a request and you expect it to come back in 5 milliseconds, but it's coming back in 2 minutes, right? Eventually the request does come back. But really, at the end of the day, you probably want to say, if it's taking 100 milliseconds, assume that it's broken and move on with life, right? Because otherwise, you have this cascading reaction of like, so system A queries system B, which then takes too long to respond, and whatever was querying system A is also then waiting, right? So you have this chain of dependencies that end up breaking, right? So by using timeouts, basically any time where you're doing anything that can basically take an unexpected amount of time, it allows you to just say, at worst, it's going to take this long, and I will either know that it's broken or not, right? The other thing I would say around timeouts is make sure you're thinking about every part of the stack when you're looking for timeouts, right? So it's easy just in your HTTP client to say like, okay, give me a timeout of 30 seconds. What is that timeout actually on? Does that include the DNS query to resolve the IP address that the host name that you're trying to look for? Depending on your library, it might not. You probably want a timeout on that DNS query as well. Does the counter on that timeout start when the TCP connection started? Does it start when the connection's established and you're just actually starting the HTTP request, right? Like, sometimes you can get away with not knowing this, but especially as you're doing more and more things, you increasingly need to kind of care about these details, so try and make sure you understand what exactly you're doing timeouts on. Fun things we've learned is when you're doing things a billion times an hour, sometimes 1% chance for things comes up kind of a lot. So just try and think through how to avoid this happening, and timeouts is a big part of that. So let's say something's timed out, something's failed. What can we do about it, right? And one of the things that, again, is not a silver bullet, but can buy you a lot of time and a lot of flexibility and help give you a lot more robustness is retries, right? So basically, whenever you make a request, it fails, try it again, right? And presumably, there's lots of things that might be factoring into it. It will be extremely difficult, if not impossible, to have a system actually know all the possible things that could go wrong and do something smart about it. So let's just be a little dumb and retry. With a few caveats. We have to be careful about doing retries, right? If we just do retries kind of naively, right, and just like, okay, I'm going to request for something, it failed, let me try it again, and try it again, and try it again, and try it again, right? You can end up in these dogpile situations where a system like has some kind of degraded performance, starts timing out, and now all the things querying it just hammer it with more and more and more retries, right? And it just falls over. Additionally, so usually you want to be able to kind of back off a little bit, take some pressure off, and a lot of how we do this a bit is with something we think of as back pressure, right? So it varies from particular situation, but if you think of like in the kind of a request style pattern, it's usually like an exponential back off in retries, right? So you request something, fails, you retry it right away, that fails too, so okay, I'm gonna wait 2 seconds, and try again, failed again, wait 5 seconds, right? And keep doing this. And this gives you a lot of things, right? So A, it just inherently lets you start taking the pressure off a system that's failing. But additionally, if you kind of relieve that back pressure gradually, right? So let's say you've gotten to the place where you're waiting like 20 seconds between retries. You fix whatever's there. If you just stop doing delays right away once you have a good request, a lot of times you can get back into the stockpile situation because let's say you had a host die that's running some system. For whatever reason, EC2 instance blipped out of existence or whatever. You've replaced it now. But let's say that system's pretty heavily dependent on caching and all your caches are cold, right? So requests are going to take longer than normal, and it's going to have more impact on the system than like when it's fully warmed up. So if you just start hammering it with all the requests right away, it's just going to fall over again because its caches are cold and can't deal with it. So by gradually relieving that back pressure, you're able to then kind of let that system warm up, let things recover nicely. And granted, you might, you have to be careful with this because you can end up having those kind of back propagating effects that we were saying if you didn't have the timeouts or whatnot. But there's a balancing act. Again, it's not going to solve all your problems, but it's going to buy you time to be able to deal with things before it impacts your users. The last thing with retries to think about is there any way to route around the failure, right? Is there any way, so like presumably in a distributed system, if you have highly available systems, there's going to be more than one host. Like if service A is querying service B, there'll be multiple hosts in service B that potentially can answer the request from service A, right? So ideally, if you make a request to a host in service B and it fails, you want the next request to go to a different host in service B on the basically hope that whatever problem is happening is isolated to that host and not the service overall, which happens a lot of time, right? Like again, say the host has a bad RAM chip or hard drive failed or whatever, right? There's a few ways you can go about doing this. You could potentially put actual load balancers between all your services. That tends to have a lot of operational overhead, but keeps your application code, keeps that logic out of your application code. Bitly, we do this basically in application. So there's an open source library that we put out called hostpool. That's a pretty straightforward Python library. I think we also have a Go version somewhere. That lets you basically do something where when you're about to make a request, in your configuration for your service, right, for service A, you instead of just having like a common name for service B, you just have all the hosts that possibly could answer a request in there. You get that out of your configuration management or whatever. You load those up into hostpool, and then when you go to make a request, you say, hey, hostpool, give me a host, right? And so it'll give you a host, so it'll kind of pick one at random. You make your request, and when you're done with the request, you give hostpool some feedback saying that request succeeded or failed on that host. And based on that feedback, hostpool will basically adjust the probabilities for each of the hosts in the pool of what host is going to give next, right? So over time, what this ends up doing is if one of those hosts starts failing, it reduces the chances that future requests are going to go to it, but it still lets a few requests go through every so often. Basically, it assumes that you're going to be doing retries. And this way, let's say, again, going through the case of a host slipped out of existence, you've reprovisioned it, things are back to normal. Since it's still occasionally sending requests to it, it can go, oh, it's back now, and basically put that back into rotation without you necessarily having to do a whole lot. So it's nice. Again, buys you time, doesn't actually fix the underlying problem. You still got to deal with that. It's also worth noting that NSQ, the clients have a lot of this type of logic built in. So PyNSQ provides a lot of tooling out of the box for doing retries and intelligent backoffs and so on. So lots of lessons learned baked in there. So definitely check it out. So one of the next kind of approaches or techniques that we've learned is really helpful in dealing with a lot of these situations, particularly around consistency, is using immutable data whenever possible, representing things in a mutable way. What do I mean by that, right? So immutable means just things that don't change, right? So in some ways, Bitly, we get to cheat, right? Because inherently our data set tends to be fairly immutable, right? Clicks never change, right? They're just a thing that happened. Similarly, shortens with the constraints that we put on them can't change, right? In some situations, you may not necessarily have that flexibility, but one of the ways that you can at least take a step towards this and have more of the data in your system be immutable is to describe the communication between your systems as events as opposed to commands, right? Saying this happened instead of go do this, right? Again, much like a lot of these other things, there's lots of other wonderful benefits for this. That's another talk. But in the cost of text of dealing with failure, and particularly dealing with consistency issues, by having your data be immutable, it eliminates a lot of the weird situations that can happen, right? So like, if you just have a series of events that happened, you can like replay those and deal with that. Or it's a lot easier to make things idempotent, right? So building a system to recognize, oh, I've seen this event already, so I don't need to care about it anymore. So like, which can happen in retries, right? A lot of times with a retry, it's unclear if the other system actually got the message or not, right? So it helps. The last piece I would talk about for dealing with these failures and making sure and keeping some sanity is monitoring, right? So again, before I mentioned, we have about 400 servers. Knowing that something is broken among that many servers is a very non-trivial problem. If you don't have monitoring in place, it's very easy for stuff to be broken and you don't even realize it. I wish I could remember who to attribute this to, but there's a great quote I've heard of: if you don't have a Nagios check on it, it's just broken and you don't know it yet, right? Unless you have something actively checking things, it is almost certainly going to break over time. So what does this end up looking like, right? So at Bitly, we happen to use Nagios. There's lots of other options out there like Sensu, or I'm sure there's more. But we also then expose it in a bunch of ways. So we have an on-call rotation. I was actually on call last night. It's a little noisy. So as you can hear, this get pushed out as text notifications saying like, hey, this broke. You should go check it out, right? So we have dashboards around the office giving an overview of what the status of our systems are. And this is great, but it's also somewhat limited, right? It's saying, hey, this thing's broken, but it's usually not saying a whole lot about why it's broken or what consequences that breakage has, right? So you still need some other tools in monitoring beyond just something doing this checking, right? So one of those is logging, right? So there's always a careful balance in logging of like, if you just log all the things, you end up with a torrential stream of stuff that you can't make heads or tails out of. But the flip side is, if you don't log enough, be like, yep, it's broken. Yep. So having appropriate level logging, that's often one of those things you kind of just have to try a bunch of things and get a feel for what's right for your system. But having logs and additionally having centralized access to logs can be very powerful, right? Again, if you have, so like our front end tier of servers is like, I don't know, 30 servers or so. Let's say a particular request, like a malformed request from a user is causing things to break. And with how the load balance is working, those requests are getting sprayed across those 30 servers. If you're trying to identify that by logging into each box and finding the requests that are causing the failure, it's going to drive you crazy, right? Because one failure will happen over here, and one failure will happen over here, and one failure will happen over here. And you'll never find the pattern in all that noise. But if you have all your logs going in a centralized place, you can look at them as a whole and understand what's going on. There's increasingly some great tools out there for, like, historically Splunk was great for this, but super expensive. There's the Elk, Elasticsearch, Logstash, and Kibana, which is open source options for this, or even just doing syslog to a single server and grepping through stuff. It's hugely useful. The last piece that we try and do is, in addition to logging and notification checking, right? We do a bunch of basically graphing, right? Capturing metrics and kind of displaying those over time. And this really helps get you that extra context of, like, at a system level, holistically, what's going on, right? So we've definitely run into situations where, so internally we call redirects decodes, right? And that's actually what these lines are about. And everything will seem like it's fine, but if you graph this, you see all of our decodes dropped by half. It's like, whoa, right? And if you have this kind of display up and you're just checking out yourself, and you're like, yep, that's broke. We should look at that. But without that visualization and kind of like human pattern recognition, it would be very hard to build a system to actually recognize that that is a problematic change in your system. So you should check it out. Some particular tools around this that are pretty useful. We use what was it? StatsD and Graphite. Thank you. Still a little early. Yes, and this actually I recently learned about is Grafana. It is a fantastic interface to Graphite. If you're used to a normal Graphite dashboard and haven't fully damaged your brain to have that be normal, you should check out Grafana. It's fantastic. So to recap, distributed systems, they're great. We love them, but we have to be careful, right? We have to, hosts fail, networks fail, so we have to be able to deal with that, right? So we want to try and make things asynchronous whenever possible. We want to have timeouts on everything. Seriously, everything. Database requests, DNS requests, HTTP requests, anything. Retry whenever possible, but be smart about it. Back off, right? Make things immutable whenever we can, and monitor all the things all the time. With that, any questions? Sure. It does. It's fair. So the question was if I could compare NSQ and ZMQ or 0MQ. So they work at different levels. 0MQ is more like a basic library for basically doing messaging over a wire between two hosts, basically, or potentially more. But it's basically a library level thing. NSQ is more a collection of tools for building distributed systems. So like you actually have like daemon processes and so on that can act independently out of the box. So they're kind of different level. And similarly, NSQ has somewhat stronger opinions about how you do things than 0MQ does, but it basically different trade-offs and slightly different purposes. But you could build NSQ using 0MQ. That makes sense. No.
So I understand your architecture is hosted, correct?
Yes.
And it's primarily virtualized.
50-50.
Okay. How quickly were you able to resolve that network problem that you discussed? As I'm assuming, since it isn't your infrastructure per se, you had to rely on others to ultimately provide the answer for you.
Ish. So for kind of more detail, so the question was how do we dig into that crazy Hadoop is an off button for Bitly problem. So that happened. So our server is split between two data centers. One's basically effectively managed colo kind of thing. The other half is in EC2. This particular problem happened in the managed colo space. So there, it was a mix of working with our hosting provider to understand what was going on the network side, as well as basically just doing a ton of logging and extra monitoring, right? So we basically just like put all of the networking stuff under a microscope, right? So basically anything we could get out of the Ethernet cards, logging or monitoring wise, we did that. And similarly over time, kind of like you normally would as part of problem solving, at first we didn't even know why it was happening, right? We were just all of a sudden half our hosts couldn't talk to the other half. We're like, whoa. What just happened, right? And then over time we're like, oh, whenever these particular links get saturated, which tends to be when a Hadoop job runs, that seems to be a trigger, right? So now that we can reproduce it, A, we can stop doing that. But B, we can like make some changes, kind of trigger it again and see like, okay, that either worked or didn't, and kind of work through it like that. But yeah, the specific answer is basically log and monitor as much as possible related to the specific problem. Cool.
What monitoring tool do you use to look at the Ethernet working on case Wireshark or something?
I'm trying to remember, to be honest. So I personally wasn't doing the detail work on that. I want to say there were a few Munin and Graphite plugins we were using to basically get like counters off the Ethernet cards and pump those into Graphite and Munin. I think in some situations we were looking at TCP, but it's mostly getting, I remember it was mostly getting counters off the Ethernet cards. Basically, so the way we ended up figuring out was these flow control packet things, is the Ethernet cards have counters for those. And ideally, those shouldn't be incrementing because we thought that was all turned off. But it was getting incremented, like, oh, well, that'll cause some problems. But it's also one of those things that's like usually a bit lower level than you're really paying attention to, so what's going on there?
So with the host pool, you mentioned that the end client that was requesting the host pool would actually send it whether it was successful or not.
Yep.
Why would that be more important than you say running a failure detector in the host pool itself?
So basically it makes it easier for things to be separated. It allows host pool to be a relatively simple library that just handles the basically like probability adjustment portion of things. And it allows each individual application to have the logic about what defines a failure, right? So with different systems, like we might have gotten an error back from the other system, but that might be okay in a certain context, right? Or we may not want to necessarily, depending on the nature of the error, like maybe that system knows enough about the response to say like, oh, that's a system level issue, not a host level issue, so I'm not going to take it out of host pool or something like that. So it basically allows the host pool to limit the knowledge it needs to have about the particular details of any one application that it's working inside of.
So does it also have a failure detector or does it not have a failure detector?
Nope. It just basically, so it's actually like it's maybe a few hundred lines of Python. It's really straightforward. So it's basically just provides an API to like load up a bunch of hosts, ask for a host, and then give feedback on whether a request to that host succeeded or failed. And that's basically all it provides. Yep.
Isn't this like failure related? What sort of bottlenecks does having a distributed system allow you to avoid or overcome?
A lot of it, really depends on the particular problem you're trying to solve. Most of the time, what it comes down to is it makes it easier to just use commodity hardware, right? So let's say you're solving some kind of problem where you need to have a whole lot of data in memory, right? If you can find a way to break up that problem that can spread over a bunch of hosts, and there's points where this makes sense, but like, so let's say up to, I don't know what and this will change over time with Moore's law, but like let's say up to, I think it's like 64 gigs at this point, right? Like having more RAM in one box doesn't dramatically cost the price, right? But once you go past a certain threshold, right? Like if you try to have one box with a terabyte of RAM, you can get that. It's gonna cost you like, I don't think Bitly even has that, like, it's gonna be like a multi-million-dollar machine, right? On the flip side, getting a cluster of like commodity hardware that has that much RAM as a whole will be much cheaper, right? So it lets you basically give that kind of flexibility. Additionally, for a lot of high availability issues, at the end of the day, you have to have a distributed system because if you don't have geographic diversity, you're not going to be highly available no matter what. So you might be using something that hides the details of it, but at the end of the day, you have a distributed system anyway. Any other? Yeah. Sure. So basically, the idea is having, it can depend on the context, it depends a lot on the context of what you're working on, right? But whenever possible, basically having it where the discrete things that you're working on don't change themselves, right? So an example that could be, that's a good way to describe this. So an example for us is, sorry, I'm trying to think of like how to balance like specific versus something more general. So I'll just go with a specific thing and we can work out from that. So for us, we know that short links never change, right? Once a short link gets created, but then it never gets edited and never gets deleted, right? Accordingly, we can structure a lot of our systems to be simpler since we don't have to deal with those update and delete cases, right? A lot of ways, update and delete often can require more specific synchronization, right? In that you're, so for example, let's say you have your data spread across, let's say five hosts, right? You're sharding your data across those hosts, right? If you're just doing creation and not dealing with update and delete, you can just spray requests at all the hosts and don't have to care about things, right? But if you're pulling an update and delete into the situation, now you have to worry about like the order that things come in, and you have to care about making sure that all the relevant requests go to the same host. And these aren't intractable problems, but if you can avoid them in the first place, it can be very nice, right? And so depending on how you're building things, there's different ways. Sometimes you can get away with it by just restructuring your data. So example, that would be somewhat different from ours. So like let's say you were dealing with like financial transactions, right? A way you could potentially approach this is instead of structuring your system where like you just have a system maintaining an ongoing balance of an account as like an authoritative number, as like the canonical representation of something. Instead, you could have whatever system is keeping track of somebody's balance just keep track of the individual transactions, right? Because those transactions are effectively immutable. The transaction will never change. Obviously, some exceptions there, but still, for the purpose of the discussion, right? And then when it needs to get the user's balance, run over those transactions and get the number at that point, right? So maybe you cache that as an optimization, but the authoritative data of like what is correct, what is the full state of the world, is those immutable transactions. So does that help a little bit? Cool. Any other questions?
What are some scenarios when load balancing makes more sense than a host pool or vice versa?
It's really a trade-off as far as kind of the expertise and where you want to spend your time. So usually the trade-off comes down to you have basically an extra moving part in your systems, right? Like you have this other component which has its own scaling and availability characteristics and so on. The nice side though is you don't need to have any logic, your application doesn't need to know anything about how that's behaving, right? So one example where you might prefer the load balancers, like let's say you have a legacy application that you don't really want to modify much, that needs to query some new system. In that case, having the load balancer lets you minimize how much modification you're making to the legacy system while still providing that layer of protection. But if you're not necessarily in that situation, then hostful kind of approach has its advantages.
So is NSQ built on top of any other existing distributed frameworks, or do you write it completely from scratch?
It's pretty much from scratch. It's built in Go. So internally, it uses a lot of Go's concurrency tools for basically managing state, I guess, within any daemon. But yeah, it's pretty much from scratch.
Do you see either specifically in NSQ or just sort of in binary distributed systems in general, sort of holes or areas for improvement for the error detection tools?
A lot really depends on the particular problems you're solving, right? So for us, obviously since we built it to solve our own problems, NSQ works really well for our problems. But example of something that happens with NSQ is it doesn't have any built-in functionality for guaranteeing the durability of a message, right? So a lot of the topology that we use for NSQ is basically we'll run basically an NSQD instance, basically the thing that actually manages the queue on every host that's publishing messages, and the consumers then just connect to each of those directly and pull messages off, right? So in that scenario, if it's nice and that eliminates bottlenecks and single points of failure, but let's say the queues have backed up for a bit and one of the producer hosts falls off the face of the planet. At that point, the messages that were still queued on that host are lost, right? And for us, since we're doing click metrics, it's okay, right? We'd prefer to not lose data, but it's really not that horrible to our business if we lose a little bit. If those were financial transactions, maybe a different story. And there's ways you could deal with that with NSQ using somewhat different topologies, but there's some other tools that maybe have some different trade-offs there, but a lot of it really depends on the situation. Any other questions? Yeah. Oh, just done? Or 5 minutes? Cool. All right, cool. Well, with that, I guess everybody will have 5 more minutes, and I'm always happy to talk afterwards. Thank you.